Okie dokie. We're back and we're talking more about the wonderful, exciting world and the joy of random variables and stochastic processes. You know, in my book that I wrote, which is called The Handbook of Fourier Analysis and Its Applications, I wanted to refer to the book as The Joy of Fourier. And when I talked to Oxford University Press, they said, "No, we can't do that. You know, that's really not a good title." Oh man, I made one of the biggest mistakes of my life by changing the book and kowtowing to their editorial editorial comments, because now the handbook of Fourier analysis and its application is kind of buried. And if you look for Fourier analysis, yeah, it shows up. But if you hear the joy of Fourier, which is what I wanted to name it, you'd remember it for your whole life. So go with your gut if you feel creative. And I felt creative like that. I wrote another book called Neural Smithing. And this was written, oh gosh, 30 years ago. And it's called Neural Smithing, and it's about how to train neural networks. And partially because of the title, I believe it's still it is still in vogue. I checked my citations, and last year that book was cited more than any other time in previous years. So in 2020, it was it was cited more than any previous year. So I think a lot of that is due to the really interesting thing called neural smithing. The other thing, if you go to Amazon.com and you put in neural smithing, you're going to get one hit, right? And I think that that would be the same thing with the joy of Fourier. But now you go there in the handbook of Fourier, you know, you get a bunch of stuff. So anyway, I'm ranting on. So let me share my screen and let's get on to it. As Adam mentioned, I guess that there were a lot of scary homeworks that I'm going to ask you to do as a midterm. I've changed my mind and decided not to have an oral this year. So I'd like to have you have a midterm. And let's go through the questions of the midterm. And these are going to be head scratching. These are not going to be trivial questions. You're going to have to dig deep a little bit into it. First one, Tammy is hosting the annual Men with Exactly Two Children Club. So these are a bunch of men that exactly have two children. And they have a convention every year, and the fathers come with their two kids to spend a week together doing activities and bonding with their kids. Tammy, who is the organizer, needs to choose a father to hand out towels in the men's shower. And he wants to engage a man who has two sons for the task. So she looks on the list of all the people registered, and she can find out if the father has at least one son. So on the list is a list of all of the Hey, we got some. My brother just delivered me some packages here. We're going to make a list of all of the men going to the conference that have a single that have at least one male child. So the other one could be female, the other one could be male. So I want you to first of all answer the question: if we know one of the children is male, what is the chance of a father at the convention has two male children? In other words, what's the probability that the second child is male? And you assume a 50-50 chance of birthing a boy or a girl. We don't want to get into any of these detailed statistics that girls are birthed more than boys or vice versa. So I will warn you that this is kind of like the Monty Python. I know two Monties in the world, Monty Python and Monty Hall, and I got the two confused. This is very akin to the Monty Hall problem. You remember with the three curtains, and the result, the outcome wasn't what you would immediately suspect. And if you go back to that Monty Hall problem and you look at the way that you work that Monty Hall problem, you'll want to work it in the same way that that this was done. And it's the same way that you work the unfinished game that Pascal and Fermat figured out. I got an interesting email the other day, last week. It was a guy that says, you know, I followed your post on mindmatters.ai, And I think I have a very simple proof for Fermat's last theorem. If you're familiar with Fermat's last theorem, he wrote in the column of his notebook, he says, I have a wonderful way to prove Fermat's last theorem. He didn't call it that, but he says, I have a wonderful way of proving this. And he wrote it in the margin. And because he wrote it in the margin, he also said, I don't have the space here to work it out, but I have a really simple proof. And I believe it was Andrew Weil, a decade or so back, came out with a proof of Fermat's last theorem. And it was pages and pages. It was a long, complicated proof. It was nothing simple at all. And the question is, was Fermat right or Fermat wrong? Somebody thinks that, well, Fermat was right because the guy was a genius and he rarely made mistakes. That means that there's a simple proof of his theorem out there. So I got this email from this guy. He says, I proved it. And I said, wow, this is kind of cool. And he said, less than a half a page. And I told him I had doubts, but I'd look at it. And I looked at it. And guess what? It's wrong. His proof was wrong. So the search goes on for the simple proof of Fermat's last theorem to see if Fermat was right. So what put me down this trail? I forget what put me down this trail, but let's get back to this. If we know one of the if we know one of the two children is male, what is the chance a father at the convention has two male children? So this one father is on the list. He has at least one male child. What's the chance that he has two male childs? And then I want you to work this one out also, because this one is not obvious at all. In addition to A, we also know that the son, that is the son that was listed, was born on an even year, 2016, 2018, 2020. If that's the case, what is the chance a father at the convention has two male children? And I will give you an answer because I think your intuition will say, you know, it's exactly the same, but no, the answer changes if you also know that the child was born on an even year. So my hint to you on this is to go back the way that you work the other problems, especially the Monty Hall problem and the unfinished problem, or the unfinished game problem, and apply that same methodology. And I think you'll come out with some results which I think will be surprising. The next thing we're going to do is we did a lot of stuff on transformation of random variables. And what I want you to do is I want you to do a synthesis problem. Usually, well, we present the transformation usually as an analysis problem. Given the probability density function of x and the g of x, then you find the probability density function of y. Here, I would like you to do the synthesis problem where you have the density function of x, the density function of y, and you're trying to find a g to transform you to one from the other one. And I would like you to do a transformation from a simple exponential in e to the minus x to a Cauchy random variable. So in other words, you're going to start out with a density function at x, which is an exponential, and then a Cauchy random variable is your final result. That's what you want to synthesize. Now, I was too lazy to look up the Cauchy distribution, but I know it was an x squared plus 1. I said where C is a constant. So how do we choose C? C is the constant that gives this an overall area of 1, the density function of 1. And I guess I kind of goofed this here, didn't I? Because this should be a y, shouldn't it? Mm-hmm. So let me change that. Okay, so this is good. The next thing I want you to do is a simple transformation on a random variable, which gives some. This is going to exercise your manipulation skills. So x and y are IID random variables on 0 and 1. So therefore, on the xy plane, it's a little pillbox from 0 to 1, from 0 to 1. and they're independent. Remember, IID stands for independent and identically distributed, and it's on 0, 1. And we're going to let Z is equal to Y raised to the 1 over X. And so given the distribution of X and Y, I'd like you to find the distribution of Z. So this is taking a two-dimensional random variable, which is material that we just covered, and transforming it into a single random variable. First thing is, over what range does a random variable Z have a non-zero probability mass? That is, if X and Y go from 0 to 1. Why did I put 1 to 0? Boy, this is why you proofread your stuff, right? If we go to 0 to 1, I mean, we're not in, where do they read backwards? Hebrew, right? This is not a Hebrew thing where they read from right to left. So it's IID uniform on 0 and 1. So if X and Y can go from 0 to 1, what interval does Z correspond to? In fact, I'll open it up. Does anybody have a knee-jerk reaction? Or is that something you want to scratch your head over? I guess it's something you want to scratch your head over, which is fine. First thing I want you to do is to compute the cumulative distribution function for Z. And does this function obey the properties of the cumulative distribution function? What I want you to do there is simply do a sanity check, okay? Does it asymptotically go to 1? Is it strictly increasing? Does it asymptotically in the negative direction go to 0? These are characteristics of the cumulative distribution function. And then I'd like you to compute the probability density function of Z and include all interval limits. In other words, just don't put down a function. If you put down a function, that function has to say this function over this interval. So it's not just enough it's not just enough to get the function. You have to stipulate the interval in which this function is applied. Then the last question is, find an example of equality for the Markov inequality and the Chebyshev inequality. In other words, we talked about the Markov inequality as less than or equal to, right? Well, that means that there's a possibility that it's equal to. I want you to find a case where it's equal to. And it doesn't have to be equal to the thing over the entire distribution. If it's equal to, if there's an equality at one point, that's okay too. And so I'd like you to investigate this. I think that this will give you some interesting results. So I will be adding a fifth question, which I am still formulating. So stay tuned for that. So let me review what I'm trying to test you on here. The first one is basic probability, and the idea of using the classic definition of probability as we applied to the Monty Hall problem and as we applied to the unfinished game problem that allowed us to compute probabilities in a sane way. And so that's the purpose of the first case. And both of these are, like the Monty Hall problem, a little bit misleading. Your intuition can mislead you if you don't sit down and work it out exactly using the technique that we did before. This next one is for a transformation on a random variable. It's a synthesis problem. So this is a one-dimensional probability density function to another one-dimensional probability density function. And that's all well and good. And we've done a lot of these. So this is testing your ability to perform that operation. You will need a bit of creativity here. You'll have to figure out a good way to perform this. And then the third one is to test your ability of transforming a two-dimensional random variable into a one-dimensional random variable. So we have a two-dimensional random variable into a one-dimensional random variable before it's one dimension into one dimension. Here it's two dimensions into two dimensions. And we see that that is indeed, that is a distinct difference. And then the last is the inequalities, the Markov and the Chebyshev inequalities. And then there will be a fifth one, and the fifth one will be on expected values. So I'm going to add a fifth one on expected values since there's nothing in here on expected values. So I think that this quiz kind of covers the elements in all of the courses, in all of the topics that we have thus far covered. maybe not the characteristic function, but we'll get to that eventually. But I think it's a good sampling. So with that, are there, well, the obvious question is, when is that due, right? And that's what I want to ask you here. When do you think it should be due? How long do you need to do this?
I would ask for at least a week, at least personally with everything going on. I wouldn't want to try and do it before Thursday.
Okay, okay, so I wouldn't do this. How about having it due the 25th? Is that okay with everybody?
Yeah, I like the 25th.
Do you? It is a good day. When are the Ides of March, by the way?
Yesterday.
Yesterday was the Ides of March?
Mm-hmm.
And 2 days ago was Pi Day, right?
Yep.
Everybody celebrate Pi Day? If they shouldn't have Pi Day, they should have Pi Second, right?
And then what, six days ago was Mario Day, I think.
What is Mario Day?
It's March 10th, so it's MARIO, Mario.
I've never heard of that. Does that have anything to do with Donkey Kong and the Mario Brothers, I wonder?
Yeah, I guess, yeah.
Okay. Yeah, that sounds like is that a Nintendo game? It sounds like a holiday Nintendo would made up.
Yep, it's Nintendo, yeah.
Yeah, well, I didn't get any Mario Day cards, so I guess I run with a group that doesn't do those sorts of things. Okay, so I think we're good. Do you have any questions on the details of this? What I will do, I don't want individual questions about these. If you do have a question, and let's wait until class, and we'll start the class, and you can ask questions about the problems, and we'll start this Thursday. So please don't wait. Well, except for Adam, he's got other things to do. But give these some thoughts and see if you have some immediate bumps. Okay.
So I do have a question on the first one already.
Sure.
With the birthdays. So we're given the birthday of the known son. I guess. So I guess that could be the older or the younger child.
No, it's the oldest child. No, it isn't the oldest child. No, each father is known to have a son, and the son is not identified as older or younger. It's just defined as a son. This is his birthday.
Yes. And there is no limitation then on when their sibling was born. They could be twins. They could be 20 years apart.
Yes.
Okay.
Yes.
Okay.
Yeah, that's also another question. If you have two males that look a lot alike that were born at the same year, at the same time, from the same mother, same year, same time, same mother, yet they weren't twins, what were they? This is akin to that idea of, you remember the five presidents problem?
Mm-hmm.
Yeah, you're trying to think of all the mathematical ways of doing it. It isn't exactly that way. Okay, you ready for the answer? They were 2/3 of a set of triplets. Oh, okay. Isn't that interesting? So that's a question you could win a bar bet if you go into bars. Okay. So with that, if there's no additional questions, yeah, please take a look at those. And I hope to have the fifth question posted by Thursday. Yeah, Theo.
Do we need to make an assumption about how old or how far back, like what the maximum age of a son could be?
No, this could be a 70-year-old father with two sons that are 50 and 52.
Okay.
Okay. That's not the spirit of the question, but I think it's within the parameters that we set out. Oh, you're muted there, Theo.
I was mumbling to myself.
Oh, okay. What did you say?
Well, I kind of went because I am stumped.
Oh, okay.
But
Well,
I'll think about
yeah, who are you talking to when you talk to yourself?
myself.
It becomes kind of a philosophical question, right? A metaphysical question. So I wonder that myself. Okay. I think this new material is not going to be covered on the test, but we need to start on it. And this is functions of a random variable. By the way, just a couple of ground rules on here. Number one, neatness counts. You have time to present this material in a neat fashion. If this was a online quiz where you had to do things in real time, sloppiness would be okay. But this, you have a lot of time. So it's the same with the homework. Please try to be neat and not have a lot of cross-outs and strange things. And of course, no other human help. You're welcome to use like Wolfram Mathematica or something like that if you think it helps you, or anything on the web. Usually you can find things on the web, and you might be able to for this, and that's okay as long as you can use what you found on the web as an explanation. I tried to make these questions so that they would not be available on the web, but you never know. Everything's on the web, right? Well, not everything. And also, you're not allowed to use Chegg. Are you familiar with Chegg, Chegg? Oh my gosh, that is a service which is driving people crazy, professors crazy for cheating. It is a website which you pay a fee, a monthly fee to use, and you submit them questions and they will get you answers. And what they do is they employ a bunch of really smart people from like backward countries, third world countries, and pay them $15 an hour. So there's really smart people. I don't know what they pay, but say $15 an hour, and they pay them for solutions to the problems. And so you can literally go into a test and right at the beginning of a test, and with your cell phone, covertly take pictures of all the problems and sit there and try to work them out. And you will, in maybe 10 or 15 or 20 minutes, get solutions to all the problems by somebody who is an expert. And this is this is kind of driving professors mad, especially on take-home tests such as this one. So you're not allowed to use Chegg, no human help, and Chegg uses human help. But if you want to check it out, it's Chegg, and they make the excuse that their purpose in life is to they make the excuse that their purpose in life is to help people with homework. So that's how they justify themselves, you know. Okay, anyway, let's start with functions of random variables. We've already talked about some of the functions of random variables. For example, I lost my magic pen. There it is. Okay. I need my magic pen if I'm going to write here. We've already talked about functions of random variables. One is the sort of problem that you're going to deal with already. We've already talked about this, which is looking at a two-dimensional or a higher dimensional random variable and looking at a density of one. And we've looked at a few of these already, such as z is equal to the maximum of x1 plus x2, right? Or we've looked at z is equal to x1 plus x2. So this is, again, taking more than one random variable and reducing it to a single random variable. So this is a joint probability density function that is reduced to a single probability density function. Now we want to do something more exciting, if you will, and look at functions of random variables. That is, we might have different values of z as a function of x. G sub k is an arbitrary version. So therefore, we might have z1 is equal to say x1 times x2. And we might have z2 is equal to x1, I don't know, minus x2. Do you get the idea? So there's two functions. So this would be the g sub 1, and this would be the g sub 2. And the problem here, of course, is given a function of x1 and x2, to find out what the density function is for f of z1, z2. So we're going through a multi-dimensional, if you will, random variable transformation. We're going to skim over this and actually skim over some of the details, but present the results and try to justify the results as a generalization of what we have seen already. One of the criteria here is that we are going to have something called invertibility. And that means that if you find a g sub k, which is a function, can you go backwards? Can you go backwards? And this is the h of k. This is kind of the inverse. Remember, we used to have a g and a g inverse, right? When we were doing stuff before. Well, now we're going to invert it, but we can't capture that in a single function. So over here, I don't know, what do you think? It isn't obvious to me, but over here, do you think we could solve for x1 in terms of z1, z2, and x2 in terms of z1 and z2? Yeah, I think we probably could. It isn't obvious to me. Well, I don't know. Maybe we. No, let's not do it. Let's not do it. I should have chosen something which is a little bit more simple. But well, let's choose one that's more simple. We have z1 is equal to x1 plus x2, and z2 is equal to x1 minus x2. And I'm choosing simple algebraic equations to make it easier. Clearly, it turns out that x1 is equal to 1/2 z1 plus z2, right? And x sub 2 is equal to 1/2 z1 minus z2. Does that make sense? I mean, you know, it's a simple solution of an algebraic equation. So this is the forward. This is the g sub k, and we will visit now these h sub k's also, which are the inverse. So the x's go to the z's, and the x's go to the z's, and down here for the h sub k's, the z's are going to go to the x's. Okay. So with that, we have exactly what I was talking about in the previous slide. We have the z sub k's, and as a function of the g sub k's, that's the forward nonlinearity. And we're going to assume what we saw before and assume invertibility, that we can invert back to the result here. Okay. This leads us to a something called the Jacobian. Now, if you remember, we did derivatives. We had to do derivatives of the transformational function as we performed our transformation on a random variable. The extension of this is something called a Jacobian. The Jacobian is a differential in multi-dimensions. You can't write integral over x dx. What we have to do in order to perform the operations is we have to have the partials of all of the variables with respect to all of the other variables. And don't forget that we have z1 is equal to g of x1, x2, all the way up to x sub n here. I mean these capitals. I didn't want to make those capitals, so I'm going to redo it here. No, I guess we can do it that way. No, that's okay. So what we would like is we would like the derivative of this with respect to x1, the derivative of this with respect to x2, the derivative with respect to xn, and that's going to give us this first row of values as we look at the partials in all of these different directions. Likewise, this would be g sub 1, by the way. Likewise, we will have z2 is equal to g sub 2, another function of x1 all the way to xn. And if we take the partial derivative of z2 with respect to, first of all, x1, x2, and x sub n, and line them up, we get the second row here. And we do that with all of the different derivatives, and we fill up this matrix, which is called the Jacobian. In terms of notation, we will refer to the Jacobian in this fashion. It is a gradient. You remember this gradient sort of operation from electromagnetics. It is a gradient sort of operation. So that we use the upside down delta. What do they call that? What's the upside down delta? Anybody know?
It's the del operator, I
Yeah,
thought.
I think del. Yeah,
Is it, it's just a del? Okay.
I think some people call it. You like say delta backwards, but I don't know how you do that. So
Yeah, I believe the result, I believe it is called Nambla. Could somebody look that up, see if that's right? The Nambla operator. Yeah, the delta has the pointy part going up.
The Wikipedia page, it says Nabla, Nabla, or the del operator.
Oh, really? Okay.
It's the del operator represented by the Nabla symbol.
Nambla. Okay. Is there an M there or not?
No, it doesn't look like it. It just Wikipedia has it as Nabla.
Okay, the Nambla.
Nabla.
You want to put an M there, don't you? Nambla. It'd be easier if I put it. So I think that's referred to as a Nambla. Anyway, so that is the transformation Jacobian. Now this is a direct generalization of what we did before. Do you remember that if we had invertibility in one dimension, that invertibility in one dimension corresponded to strictly increasing or strictly decreasing? That's the only way you can have invertibility in one dimension, right? I'm trying to think of other ways to have invertibility, but I can't. So invertibility is either strictly increasing or strictly decreasing, and then you have invertibility. And if you recall, we performed the operation, we went through all of the math, and we obtained this result. And this takes the place of the G inverse that we had before. This plate takes the place of the G inverse, except it's an inverse function. It's an inverse operation as opposed to an inverse function. And then recall that we had to divide by the derivative. We had to divide by the derivative of the G inverse function, which is here. So the derivative of the G inverse function takes the place of the Jacobian, except notice these absolute values here. These absolute values correspond to the determinant. Now before, if you remember, we divided by the magnitude of G inverse. We divided by the magnitude of G inverse, or we divided by the magnitude of the derivative of G inverse. Now we're dividing by the Jacobian, the magnitude of the Jacobian. And if you have a matrix, the way that you take the magnitude is by performing a determinant on the matrix. This is going to become more clear as we do an example here. Now, you remember we showed that the derivative of G at a point was equivalent to the derivative of G inverse at the same point. I took a piece of paper and I held it up and then I flipped it over and I showed that the derivative of one direction was the inverse of the derivative of the other direction of the inverse. This is a similar thing happening here, that the determinant of this Jacobian, that is the Jacobian of x with respect to z, is 1 over the Jacobian of z with respect to x. So we can correspondingly compute either one of these, whichever is the most convenient, if you will. Okay, that's the mathematics. Now it's a little bit fuzzy where it came from, and we're not going to go into the derivation of it, but this is the generalization of the idea and gives us the equations that we need to apply to a transformation on a random variable. Here is the result if we take into account this this inversion. We get this result, and man, this looks all wrong. This should be an x, and I think everything else is right. No, that should be a z. That should be a z. That's right. That should be a z. Oh no, this is right. What bothered me is that there needed to be a little vector on top of here, because you notice that there's a vector here, but there's not a vector here. Okay, with that, let's well, I will point out the one-dimensional transformation is a special case of what goes on here. Let's take into account, I think, a very important problem with nice application, and that is if you have a random variable in x and y. So in other words, your random variable exists in Cartesian coordinates as a value of x and y. You would like to place it in polar coordinates. You would like to place it in polar coordinates. Now, where would this be important? Well, it's important, for example, if you have a, say, for example, a Gaussian random variable. And this, by the way, has application of an ideal gas, a particle in an ideal gas. Its motion, you take a particle in an ideal gas, its motion in any direction is, well, it turns out to be a Gaussian random variable. So the velocity is a Gaussian random variable at an arbitrary angle. It could be a Gaussian random variable in this direction, Gaussian random variable in this direction, or a Gaussian random variable in this direction, right? It's a Gaussian random variable. So this might be the velocity. Now the velocity requires an x component and a y component. What if you're not interested in the velocity, but you're interested in the speed of each particle? The speed, if you recall, is equal to the velocity without information to direction. So we're only going to look at the speed. You would want to look at the magnitude of this particle velocity here. You would want to look at the magnitude of this particle velocity. And maybe you'd also like to know the angle here that this particle velocity went to, right? We might call it theta. Now, in this example, we're calling it W. So that's what we have here. And V, you can see, is chosen as a velocity. And there's going to be a velocity in the x direction, and the velocity in the x direction is going to be capital X. The velocity in the y direction is going to be capital Y. And so the speed, I shouldn't have chosen this as the V, should I? I should have used it as an S variable, but this is the speed, right? The speed is equal to the square root of x squared plus y squared. That's the magnitude in polar coordinates. Likewise, the angle in polar coordinates is the arctangent of y over x. So here we have a transformation on a random variable. We're taking an xy. This is the polar coordinates, and we're transforming to an f of VW. In other words, these are the rectangular coordinates. Now we'd like to talk about the random variables in terms of their speed and their angle. Their speed and their angle. So this is the forward. Can we invert this? Yes, obviously. This is well known. We can invert this. This gives us X and Y going to V and U. Can we get from V to U, V and U? Can we get this to X and Y? In other words, what's the inverse function for this? Well, if this is the forward function, the inverse function getting X and Y back is through the simple trig operations. Okay, so we have the forward equations, we have the backward equations. What can we do? First of all, we got that Jacobian. So let's do the Jacobian. This is the Jacobian here. And the Jacobian is, if you look at the derivatives, and we're going to do the derivatives of X and Y, okay? So we're going to do the derivative of X with respect to V, and then the derivative of X with respect to W. And if we perform that operation, we get something which looks like this. This is the Jacobian. Now, in performing the random variable transformation, we want to perform what? We want to perform the determinant of this. So we take this times this minus this times this. We all know how to do a 2-by-2 determinant. And this turns out to be the magnitude of nu, right? Cosine squared plus sine squared is equal to 1, right? And we're left with the common value of nu. So the magnitude of the Jacobian is equal to the magnitude of nu, or V here. I think I switched notation from nu to V, but they both kind of look the same, so we're okay. We can say that this is, the magnitude is the same as the value without the absolute value, because we know that the speed is always going to be non-negative, right? And because it's always non-negative, we don't have to worry about the absolute value side. So let's look at the case, and this comes from, I believe, the Maxwell-Boltzmann distribution about ideal gases, is that the velocity of every particle is Gaussian. Okay, if you look at the X component and you look at the Y component, they're both Gaussian and they both have the same standard deviation. So this is what the two-dimensional probability density function would look like for a Gaussian. This is a Gaussian with zero mean. We would assume that we had a particle that was spinning around all over the place, that the average value of that velocity would be 0, right? It could go this direction as much as it can go this direction. We don't have to worry about that. So now we simply have to substitute in the formula that we had before. Question, Justin? No? Okay. By the way, what is sigma related to if we get into the physics? What changes the standard deviation of the velocity of a gas?
Be the temperature?
Yeah, the temperature, right? If you have a high temperature, your gas particles are going to be going at higher velocities than if they are at a cold temperature. In fact, sigma squared is related to, or the variance is related to KT, Boltzmann's constant times the temperature, if you remember back from physics. So as the temperature goes up, the sigma goes up. We're not interested in that for this analysis, but if you were to apply this to the problem of the velocity of an ideal gas, that's exactly what you would get. You would get a KT. Okay, so now we have to substitute this. This is our f sub x of y. So now we have to substitute into the f of x of y new. This is the first function. This is the second function, right? This is the x component. This is the y component as a function of nu and w. And that turns out to be, okay, let's do the little math here. We just plug and chug. And we obtained the following equation if we just do a blind substitution. However, the thing is that in the exponent here, we have this cosine squared plus sine squared visiting us again. And of course, that cosine squared plus sine squared, when we factor it out, is equal to 1, correct? And so we are left with this as the final distribution. And we have to be careful here because there's two variables that we're keeping track of. We're keeping track of what? The magnitude and the phase. Well, the magnitude has to be greater than 0, hence the use of a unit step here, right? That's a unit step. Now for the phase, which is the W variable, my goodness, notice that nothing in here is a function of W. Where did the W's go? The W's disappeared when we added the cosine squared and the sine squared. The W's disappeared. And so the only conclusion we have is that W now is uniform over the interval from 0 to 2 pi. And that does make sense, doesn't it? Right? The velocity could be anywhere from 0 degrees to 2 pi. That the angle, if you will, of this gas. This is, by the way, a 2-dimensional gas. Same sort of process handles in 3 dimensions. The math is a little bit uglier though. So for this 2-dimensional gas, it's between 0 and 2 pi, and it's uniform. So this is interesting because this means that the two things are independent. Let me go back here. The two things are independent because the density function for for V and W is equal to one probability density function. This is one probability density function times another probability density function. And let's talk about this for a second. You notice that first of all, if we look up here, that X and Y, that is the X component and the Y component of the velocity, are independent of each other. We can write this as one Gaussian times another Gaussian, right? We could write this as one Gaussian times another Gaussian. So X and Y are independent. And doesn't that make sense that your velocity in the X direction is going to be independent of your velocity in the Y direction? Kind of makes sense, doesn't it? In the same way, what about your speed and your angle? Should the speed be statistically independent from the angle? Yeah, it kind of makes sense that one has nothing to do with the other one, right? So indeed, that's what we see. And we can, if you want to, we can marginalize, or we can take this joint density function and we can integrate out the angle. And if we integrate out the angle, we get this result. And if we integrate out the angle, that turns out to be a distribution known as a Raleigh distribution, or a Rayleigh. Is it Rayleigh or Raleigh?
I've always said Raleigh.
Raleigh. Okay, Raleigh. It's a Raleigh distribution. I've heard it both ways, but I suspect that one of them is wrong. So we do have this Raleigh distribution, which is a common distribution. So that means the speed of a gas particle in an ideal gas, an ideal 2-dimensional gas, if you will, is a Raleigh random variable, if you're not interested in the phase. If, on the other hand, you integrate out the Raleigh, you integrate out the other way, you find out that the density function for W is uniform. It's equal to 1 over 2 pi over the interval from 0 to 2 pi. So therefore, we see that the application of this 2-dimensional random variable transformation to another 2-dimensional random variable transformation translates 2 independent Gaussians to an independent Raleigh times a uniform probability density function. So this is useful if you're interested in the speed as opposed to the velocity of something in an ideal gas or something equivalent. This could, of course, be applied to other probability density functions, but this is a nice result. Number one, because it's applicable. Number two is because the math follows very nicely. Now, there is another aspect called the the auxiliary function. I'm not going to cover that here. We're going to wait and we're going to cover that when we do sums, because I think it would be better introduced as sums. And it's really interesting. Historically, I believe this was used by Gossett in the derivation of the student T random variable, which if you've had an undergraduate course in probability and statistics, you've probably seen the student T random variable. No, I want to discard my ink annotations. Okay, this one is G. I want to go to H now. Here we go to H. Okay, this is sums of long-term and short-term random variables. We talked about doing a Z is equal to some function.
Dr. Marks?
Yes. Oh, am I not sharing my screen?
No, you are. I
am.
just tried to go download the AH PowerPoint, and there's a 404 error.
Okay, I will refresh that immediately after class.
Thank you. Sorry about that.
Okay. No, that's my fault. Thanks for pointing that out. Okay, we just talked about this sort of transformation, right? Where we took a multidimensional random variable and we contracted it into a single random variable. What would be more simple than just adding these together? I mean, that could be a G1 random variable, right? That's a very special case. And just a general rule in engineering is that the more specific a model is, the more analysis you can do with it. If you try to keep things general, you can only show general stuff. But if you get very specific in your applications, there's a lot more interesting things that you can choose. An example of that is systems. When you do systems, say you had a system. This is interesting stuff. Say you had a system and you wanted to characterize that system. How would you characterize that system? In other words, you had a system and it was a black box, and you had an input and you had a corresponding output, and you wanted to characterize that system to totally define it. In general, what you would have to do is do what? You would have to figure out all of the outputs for all of the inputs, right? It's just too much. So therefore we have to constrain the system. And by constraining the system, we get a more general operation. One of the ways of constraining the system is to make it linear. And we are all familiar with linear systems. And if the system is linear, we know that it can be characterized very easily. If the system is both linear and time invariant, or an LTI system, boy, we can do a lot with that. All of a sudden, Fourier analysis comes in, convolution comes in, and all of these other things come in. So the more specific that you can make a model, the more mileage that you'll get out of it in general. And we'll find this is the case also with stochastic processes. We can't just say, okay, here's a stochastic process. We have to talk about classes of stochastic processes, just like we talk about classes of systems. And if we talk about classes of stochastic processes, then we can get some mileage out of it. Okay. So getting back to this. Every time I do something, I got to move everything around. Okay, going back to this, it turns out that this is a much simpler a much more specified combination than here. And so we're going to do this. This is the sums of random variables. And this is going to be very interesting in terms of its application to a number of different results, because it's something we use all the time. We use the average, which is the sum of the random variables divided by the total observations. So let's take a look at this. This is the sum of the random variables. And if we take the expected value of the sum, that's also the expected value of this. And the expected value, here we go, is a linear operation. The expected value of the sum is the sum of the expected values. So we can move the expected value operation inside the summation, and we get the expected value of the sum. Remember the notation we use, S bar is equal to the same thing as the expected value of the sum. It's just a shorthand notation. So S bar is equal to the summation of the individual means. And if we add up all of those means and they're all the same, if we assume that they're IID, in other words, identically distributed and independent, that means that all of these X sub Ks, all of these expected value of X sub Ks, if they're all the same, they all have the same mean, which is XK is equal to X bar. So the sum is equal to N X bar. So that's what happens when you add up a bunch of random variables. Well, if they're IID random variables, you just take the mean and you multiply it by N, and that's the expected value of the sum of the random variables. And notice there is no assumption. Well, yeah, I guess there is assumption of independence here. But this equation is true, and it doesn't matter if they're independent. Doesn't matter if you add up a number of random variables that are not independent. This result is applicable. Only when you require independence can you come down here and just make it N times X bar. What about the variance? Oh boy. Okay. The variance of the sum of the random variables. Remember, S is a statistic, right? X is a random variable. It has a probability density function. It has a mean. It has a standard deviation. It has everything else that you're looking for. So the variance of the random variable, this is the definition of the variance. This is the definition of the variance. And now we're going to take the value of the sum and we're going to place it in here. So this, the first entry is the sum. The second one is the expected value of the sum, which we said was the sum of the expected values, right? Now, it turns out that we can factor this into the product of two summations because we sum these values squared. So it's equal to this times this, right? That's what that means, squared. It's equal to this times this. So we're going to write this first one down here, and we're going to use a subscript of L because we have to be careful. We're going to use the subscript of K over here because we don't want this dummy variable L to be different. We don't want it to be the same as the K over here, so we make it different. And then we do the cross multiplication and we get this result. We can take these summations outside and we get this result. And this is kind of cool because this is the covariance. This is the covariance. So if you recall the covariance matrix, we can have a covariance matrix. Which is equal to this. Now, if you remember, in the multi-dimensional Gaussian random variable, where we did the expression of the Gaussian probability density function, there was a big K inverse there. And that K inverse was the covariance matrix. So this is going to be a covariance matrix, and this covariance matrix is going to have the covariance matrix of 1, 1, 1, 2, all the way up to 1. Let's see, how many do we have in here? 1n, and then all the way down here to nn. You know how matrices are put together, right? And so this is the covariance matrix, where each one of these elements corresponds to a different indexed value of this covariance. So what does this say? This says to get the variance of a random variable S, you can look at the covariance matrix and you can do what? You can add all these up. It's this plus this plus this plus this plus this plus this plus this. And if you add all of those covariances up, that turns out to be the variance of the random variable from the covariance matrix. That's one way to do it. So that's interesting. Now, in doing this, there's no assumption of independence at all. We haven't made any element of any assumption of independence. But if we do make an independence, if we do make independent random variables, then it turns out that the covariance matrix is given by this. And what this means that is that this covariance matrix K is going to have sigma 1 squared, sigma 2 squared, sigma n squared, and everything off diagonal is going to be a big 0. Because the covariance of independent random variables is 0. They're not related to each other. So this is the matrix interpretation. This is the matrix interpretation of this equation. And this delta here is something called the Kronecker delta. It's equal to 1 for k is equal to 0. It's equal to 0 for k is not equal to 0. So if you apply this, you get exactly the same result here. So I don't know if you like to visualize things in matrices. I kind of like the matrix representation better than I do the Kronecker deltas, but they're both doing exactly the same thing. So if you remember that we want to add up all of the elements in the covariance matrix in order to get the variance of our random variables. And so now if we add them up, we just have to add the diagonals. Everything else is 0. So we just add up the variances. And this is something which you probably already know, that if you add 2 random variables, you add their variances together and you add their means. If you add 3 independent random variables, you add their means, and that's the mean of the sum of the 3, and you add the 3 variances, and that's the variance of the total random variable. This is kind of interesting from a convolutional viewpoint. You kind of know from your experience that if you have something convolved with something else, that new thing is going to be spread out. Usually convolution has a spreading operation, right? And we know if we add 2 independent random variables, we convolve their density functions so that convolution is spread out. What does that mean, that spreading out in terms of variance? That means that the variance is larger, right? And in fact, the variance here, this is going to be sigma 1. This is going to be sigma 2 as a measure of the dispersion of how much it's spread out. And over here, we're going to have a dispersion of the square root of sigma 1 squared plus sigma 2 squared. That's going to be the standard deviation here. So variances add for independent random variables, and also the means add for independent random variables. If you think about it, it's pretty intuitive that that is indeed the result. Okay, so here is the summary. Well, I don't know what that is. That, I think that's a repeat of a previous slide. Now let's look at this a little bit. In terms of characteristic functions, this is really nice. If you add up a bunch of IID random variables, you get the sum is equal to the summation of all of the independent random variables. So what do we know about the probability density functions? They all convolve together, right? Convolution in one domain corresponds to multiplication in the other domain. So that's equivalent to taking the characteristic function in the frequency domain and simply raising it to the nth power, right? Equivalently, if you remember the second characteristic function, that is the log of the first characteristic function, then that's given by this expression. So that's an interesting interpretation of the sum of IID random variables in the frequency domain in terms of the characteristic function and the second characteristic function. This allows us to do, well, okay, here, this is something that we've seen before, that because of this raising to the nth power, we have all of these types of random variables conserved when we add them together. So if we add, for example, in the second case here, we add a bunch of Poissons together, we're going to get a Poisson random variable, but that random variable is going to have different parameters, right? So we've seen this before and we've done it before, but this is just another realization of it here. This leads us into the average. Now this is what we typically do. If we have a list of data, we would like to find out the sample average or the sample mean, or that's also referred to as the average. And what we would like to do is we're hoping that this sample average will approximately be the expected value of X. We hope that's the case. If we take an average, we're going to get closer and closer to the mean. So this is the average. This is the mean. The average is a random variable. It's a sum of random variables, so it itself is a random variable. But the mean is a number. It's a simple number. It's the truth underlying the random variable. And I think that we'll probably stop here because we're just about out of time. And we'll start with the average next time and show some fascinating things. We'll show the law of large numbers. And the law of large numbers is intuitive. It says that the limit of the average as your number of samples increases is equal to your mean. And we have to define what we mean by equal here. Because it could be all of your samples are just outliers. It could be that you just got bad data, right? And so there could be cases where the average doesn't go to the mean. So what do we mean by this equality sign here? And we'll talk about that more next time. So with that, are there any questions? Okay, well, that sounds good. I will upload the slides or download the slides, upload the slides within a half hour. And so I guess that concludes our get together. So hearing no questions, let me go ahead and stop the share. And